Welcome back, everyone. Today we're going to talk about solutions, and in particular we're going to talk about solutions at the dilute limit. Let's start with a little bit of a definition of the terms we're using. So a solution is basically a mixture of the kind that we've been talking about the last couple of lectures, but one where one of the substances is the dominant substance, and we call that the solvent. That's the dominant substance. And then there is one or more less dominant substances, which we call the solutes. And in the case of dilute solutions, there's very, very, very much less of the solutes than there are of the solvents. In particular, we're going to examine a limit today where we're talking about solutes which are so dilute that basically each solute molecule is always surrounded by solvent molecules. In other words, we have a situation like this where the solutes, which are the darker triangles here, never interact directly with each other. They only are ever surrounded by solvent molecules. And this limit simplifies a few things. It allows us to make a more predictive analysis from a sort of straight up pencil and paper standpoint. We can solve for certain properties of these dilute solutions analytically. And in particular, because we're in the limit where the solute molecules are isolated from each other, surrounded only by solvent, then the solute molecules never interact with each other, and the system behaves a little bit like an ideal gas, where again, the gas particles don't ever interact with each other. In this case, it's the solute molecules never interact with each other. They can interact with the solvent, and the solvent molecules can interact with the solvent, but we never get solute-solute interaction. All right, so to investigate how these will behave, we need to understand the chemical potentials involved. And we're going to start from the limit of just a pure solvent, right? And so in the case of a pure solvent, the Gibbs free energy is just the number of solvent molecules Na times the chemical potential of the pure substance, which in principle is a function of temperature and pressure. So this is the Gibbs free energy of our pure solvent, and that's going to be our A substance. And to this pure solvent, to this substance of pure A, we're going to add a single 1B molecule and see how that affects the free energy. See how that affects our material. So the change in the Gibbs free energy, well, that's going to be some change in the internal energy of our system plus P times dV term minus AT ds term. And these first two, they don't depend on the number of solvent molecules. They can depend on the interaction between the B molecule and its nearest neighbors, but not in general on how big, how large an amount of solvent we have in total. We've added one B molecule to this solvent, and so it's only in the region near the B molecule that the solvent will be affected, and so that can change the internal energy of our system. That can change, for instance, the volume of our system or the pressure in our system. But it's not going to depend on how big the system is, how many solvent molecules there are. Again, these interactions only take place over short distances between B and its nearest neighbor. Similarly, part of the entropy term is also independent of the total number of particles in the solvent, because again, that entropy term will have to do with the interaction of B and its nearest neighbors. But there is at least one term that will show up in the entropy, which does in fact depend on the size of the system, and that's the choice of where in our great big system we've placed our single B molecule. And obviously, if we're going to have a system of sort of sites for molecules to go in this solvent, then the multiplicity or the number of choices that we have in where we put our 1B molecule will be proportional to the total number of solvent molecules. So this ds term, the change in the entropy term, will have a proportionality which is, or a multiplicity which is proportional to the number of particles. So that's going to have a term here of k logarithm of the number of solvent molecules, plus a bunch of other terms independent of m. Right, so we have terms that are independent of the size of the solvent system in the entropy, and we have terms that are independent of the size of the solvent system in the energy and PDV terms, plus we have this one term here which does depend explicitly on the number of particles in our system. So we could write the change in the Gibbs free energy by adding a single particle to it, or a single molecule of the solute to it, as some function, again, of just the temperature and the pressure, independent of the number of solvent molecules. So these are independent of Na, minus an explicit dependence kt times the logarithm of Na, where this t here comes from the t ds. So we take this ds term, we multiply it by t, that gives us this third term in the change of the Gibbs free energy. And we've sucked up these plus these into this arbitrary function, which is a function of temperature and pressure. All right, so this is the change in the Gibbs free energy for adding a single solute molecule B to the system. All right, so that's step one. The next question is, how does it change if we add not one, but two molecules? So now what about 2 molecules of solute B? Okay. Well, the tempting thing to think of, well, is that if one molecule changed our Gibbs free energy by this amount, how much would adding a second molecule change our Gibbs free energy? Could we just double this term? And the answer is not quite. Almost, but not quite. So we can't quite just say dg is twice this function of temperature and pressure minus twice kT log Na. And the reason is, well, okay, obviously these ones should be just fine because we're going to have 2 B molecules separated far apart from one another. So BB interactions aren't going to happen. It's just B1 interacting with its nearest neighbors and B2 over here interacting with its nearest neighbors. And so this interaction term, this term which has to do with the local interactions between our solvent molecules and solute molecules, that indeed will just scale with the number of molecules to interact with. But this term over here, which again represents the added entropy of where are you going to put those 2 molecules, and here we have an effect that we first saw when we were looking at the ideal gas, which is that because the 2 molecules are indistinguishable from one another, that this orientation and that orientation we can't tell the difference between, right? So if we swap those 2 molecules positions, we have identical situation with our material. And so by just doubling the multiplicity here directly, we have in fact overcounted by exactly a factor of 2. And so we would then have to subtract from this entropy term, which in this case is going to be an addition because this the entropy term comes as a minus. We're going to have to add in this kT natural log of 2 because this is essentially what happens when we divide the multiplicity that we had doubled here. We have to divide that by a factor of 2 because we've double counted the switching. Okay, and again, this is a familiar addition that we had to add again when we looked at the ideal gas law. Because these are indistinguishable particles, this is a sort of a familiar correction factor, and the same familiar story will play out when we want to look at 3 molecules, for instance. Whoops. Pardon me. If we wanted to add 3 molecules to our material, looks like my mic's a little bit hot there. If we wanted to add 3 molecules to our of solute to our solvent, then we would have 3 locations, 1, 2, 3, with indistinguishable particles in them. So there would be 3 ways that we could exchange the first particle, whichever one we decide, or indeed which one did we want to call particle 1. We had 3 ways to arrange for that, and for each of those 3 ways we would have 2 ways to label particles 2 and 3. So the total overcounting would be 3 times 2, or 6, and the pattern here is obviously for each added molecule we add, we go a 3 times 2 times 1, and then for 4 it would be 4 times 3 times 2 times 1. So what we have here ultimately is a factorial term to deal with the overcounting. And so for NB molecules of solute, we're going to have a total change in the Gibbs free energy of NB times whatever that local interaction function is. Again, this F of T and P here accounts for all of the local interactions between a single solute molecule and its nearby solvent neighbors, minus this NB KT log NA plus KT log NB factorial, where this is a entropy term that corresponds to the number of different ways in our solvent A that we could arrange for NB molecules of solute to be arranged in that solvent. And if we can further extrapolate this by if we have a large number of solute molecules so that NB is large, then we can apply Stirling's approximation here so that KT log of NB factorial would be approximately KT times NB log NB minus NB, or we could pull the NB, factor the NB out then, and it's going to be KT, or sorry, NB KT, let's put it out front like we usually would, times logarithm of NB minus 1, giving us a total Gibbs free energy here, a total change in the Gibbs free energy of NB times some function of temperature and pressure minus NB KT logarithm of NA and plus NB KT times logarithm of NB and minus NB KT. And this again requires that NB is much, much less than NA. In other words, that we're in the dilute limit, and we get away with this because the B's aren't interacting with each other, and so we can limit ourselves to just NB times the local interaction of a single B with its neighbors. If we weren't in this dilute limit, then this first term here would be very much more complicated because we would have to start accounting for the local BB interactions with one another, and that would definitely not be a simple function of temperature and pressure. It would also depend on the density of the B molecules, how close on average they were getting to one another, and that would make this very much more complicated. So in the dilute region, or in the dilute limit, this is relatively simple, but for in the not dilute, in the non-dilute limit, I guess, this gets very much more complicated. This whole analysis has been done under with just a single solute, but there's nothing in here that that would prevent us from saying that we could go through this whole procedure again for multiple solutes. We would just add terms in NC and terms in ND and etc. etc., etc., for each of the other solutes. As long as they were all in the dilute limit, we would end up with the same thing. Okay, so now that we have calculated how the Gibbs free energy of our mixture, of our solution, will change with the addition of some number NB solute molecules, then to calculate the chemical potential of the A and B substances, we just apply our definition here of chemical potential, or one of them. UA here is going to be the partial derivative of G, of our Gibbs free energy, with respect to Na, holding temperature, pressure, and the number of solute molecules constant. And so if we look up there, that's going to be our original chemical potential of our pure substance at that temperature and pressure, minus, so in other words, the original G, it does depend on Na, right? And to this G, we've added a dG. So this term up here gives us this term to the derivative. And then we look in here for the explicit Na dependence, and the only place it shows up here is in this second term. And that's going to be a derivative of log Na, or in other words, just minus NBKT over Na. All right, so this is the chemical potential, the modified chemical potential of our solvent. And what we can see here is that as you add more and more solute to our material, it's going to decrease the chemical potential of our solvent. If we do the same for the chemical potential of our solvents, our solutes, again dG, this time in terms of NB, holding temperature, pressure, and the amount of solvent constant, there isn't any explicit B dependence on the original pure solvent Gibbs free energy, obviously. So it's just in here that we get our explicit dependence on the number of B molecules. This first term just gives us that function, again, at this point unknown, of T and P plus a KT logarithm of NB over NA term. So this is the chemical potential of our B or our solute molecules. It's conventional often to write this in terms of molality. So the molality M is defined as the number of moles of our solute divided by the mass in kilograms of our solvent, which is this ratio, the number of B molecules and the number of A molecules multiplied by some constant. So it's some constant times NB over NA. And if we absorb this constant into that function f and rename it such that the chemical potential of B is our mu naught T of T and P plus KT T times the logarithm of our molality, where this chemical potential mu naught here is the chemical potential of our or of our solute at molality equal 1. So if we let m equal 1, then this second term disappears, and this is basically a reference chemical potential that could be looked up in various tables for a given molality of, or for a molality of 1, a sort of a standard a standard solution, if you will. All right, so now that we've established how to calculate chemical potentials for the solute and the solvent in solution, what can we do with this tool? Well, let's consider first the process of osmosis. So imagine that we have a system here where we have a pure solvent on the left of our system and a solution, a dilute solution of that same that same solvent with some amount of solute in it. And separating the pure solvent from its solution, we have some form of semi-permeable membrane that allows the solute or solvent molecules to pass across that membrane, but doesn't allow the typically larger solute molecules to pass. So it filters out basically the solute from the solvent. So what's going to happen in this system is that, again, since the solution for the chemical potential, or so since this chemical potential of the solvent in solution is the chemical potential of the pure solvent minus some term here which has to do with the ratio of the chemical or of the number of solvent molecules to the number of solute molecules. Any amount of solute is going to lower the chemical potential of our solvent. And if we're working at fixed temperature and fixed pressure, then lowering the chemical potential is akin to lowering the Gibbs free energy. Again, we're not dramatically changing the internal energy of our system with this addition as well. So since the system is going to since the chemical potential of our solvent is lower in the solution than it is in the pure form, and since the system wants to minimize its Gibbs free energy, therefore particles will tend to drift towards lower chemical potential. That's just going to be the trend. So the result of this is that the solvent molecules are going to tend to drift through this semi-permeable membrane. In other words, the solution is going to pull some amount of pure solvent into it, but that flow is going to be one directional. Another way that we could think about this is that it makes sense that we're going to have a net drift of solvent molecules across this membrane because the rate at which solvent molecules will fall through the holes from left to right is larger than the rate at which solvent molecules will fall through the holes from right to left, because sometimes it won't be a solvent molecule running into the barrier, but a solute molecule running into the barrier. While every time there's a collision with the barrier from the left, it's always a solvent molecule, which are allowed to go through the membrane. But sometimes for collisions from the right, the thing colliding with it will be a solute molecule, which isn't allowed to pass through the membrane. So there's even a microphysical reasoning for why in this case we would have a drift from the pure substance into the solution. This is a process we call osmosis. And if you want to have a sense of how important is this osmosis, how big an effect is this osmosis, how strong is this pull towards the of the pure substance or pure solvent into the solution, then what we could do is try and calculate, well, how would you stop this process from happening? And to stop the flow, we would need to apply some sort of a back pressure from the solution into the pure substance. In other words, the pressure here in the pure solvent would have to be less than the pressure in solution. And indeed, the solvent would sort of flow across that boundary, and as it does so, it's going to leave more solvent over here than it did over there, and so you might even expect that the pressure would increase on this side if you had a constant volume, for instance. But in any case, we could measure the difference in pressure from the solution side to the solvent side, and that would be a measure of how strong this effect is. Well, the equilibrium condition that we're not going to get any more spontaneous drift from one side to the other is that the chemical potential is the same. So the chemical potential on the left, that's the pure solvent, is just going to be our mu naught times the temperature and pressure 1, the pressure on that pure solvent side. Whereas the chemical potential on the right, that's going to be our solution chemical potential, which is mu naught times temperature and whatever the pressure is on the right-hand side, minus this correction factor, NBKT over NA, for the presence of those B molecules. So this is the equilibrium condition, and if we can calculate a value for the two pressures there, then we could calculate the difference in pressure that osmosis, the difference in the effective difference in what we would call the osmosis pressure. And we're going to make an assumption here that this isn't a huge effect. Again, this is in the dilute limit, so that the number of B molecules should be very much lower than the number of A molecules. And so this correction term shouldn't be huge, which would imply that the two pressures should be reasonably close. And so we're going to, under that assumption, expand our chemical potential here in essentially a truncated Taylor series. We're going to make a linear approximation that the chemical potential at temperature and pressure 2 is approximately the chemical potential at temperature and pressure 1 plus a linear pressure term P2 minus P1 times the derivative of the chemical potential with respect to pressure. Again, this is essentially a first-order Taylor series approximation. We're going to make the assumption that this pressure difference isn't huge, and that would give us just the single derivative term. Obviously, you could take if the pressure difference was larger, you could expand this potentially to include more higher order terms, but we're just going to keep it in the linear regime here again, assuming here that we're in the dilute limit so that the changes will be relatively small. All right, so if we take this expansion of our chemical potential and put it back into our equilibrium equation, mu naught T and P1 is approximately mu naught T1 T at P1 plus P2 minus P1 d mu naught dP, and then minus NB KT over NA. And obviously these first two terms cancel out, and we could rewrite this as the pressure difference times d mu naught dP is equal to NBKT over NA. Notice that mu naught, which is the chemical potential for a pure substance, could be written as G over N, again, Na being the number of particles of our pure substance, and Na times the chemical potential of our pure substance would give us the Gibbs free energy. And so d mu naught dP is going to be the derivative of G over N dP, and that's going to be 1 over N dG dP, and dG dP is the volume, so this whole thing is volume over N. So in other words, this d mu dP term just gives us a factor of V over N, and if we plug that back in over here, we can say that the pressure 2 minus pressure 1, the change in pressure, the pressure difference, is V over the number of solvent molecules, and that's got to be NBKT over the number of solvent molecules. And therefore, canceling out those NAs, we can say that the pressure difference is NBKT over the volume, or if we wanted to write it in terms of moles, it would be little nb times RT over the volume. We call this the osmotic pressure, and it's the pressure required to stop osmosis, the pressure required in the solution to stop osmosis from happening, to stop it pulling pure solvent across the membrane. And this whole expression here is known as Van 't Hoff's formula. And again, can be used to calculate the effects of osmosis in a variety of situations, from cellular membranes to various forms of filtering, desalination, and so on. And there's a couple of homework problems there are a couple of problems in the text that are interesting to look at and that we will examine in a future homework. All right. Well, another way that we could use these chemical potentials of the solution, dilute solutions, is to examine the effect of putting a little bit of solution, dissolving a little bit of a solute into a solution, the effect that would have on the freezing and boiling points over the phase transition points for our pure substance, for our pure solvent. So we're going to be examining this again in the dilute limit, and in particular, we're going to also assume here that the boiling. We're going to examine the boiling point, and we're going to assume here that the boiling point happens such that the solvent dissolves, or the solvent boils off, but that the boiling point for our solute is significantly different, and so that the solute, the stuff in the solution, dissolved into solution, that's not boiling off. It's just the solvent that's boiling off. So for instance, salt water, if you're boiling salt water, the salt isn't boiling off into the steam is pure water. And so the salt molecules or the salt radicals are staying in the solution as the solvent boils off. And so we're going to examine this limit here of looking at what happens to the boiling point of our solvent in the context that there is some solute boiled into it, or some solute dissolved into it. So we're going to consider a dilute solution, and this dilute solution is right at its boiling point. And again, that we're going to say that the gas phase of this, the stuff that's boiling off, is pure pure solvent, and so that the again the right at the boiling point, we're going to be in the situation where the equilibrium condition is going to be that the chemical potential of our solvent in the liquid phase at T and P, or the chemical potential in our liquid phase, is going to be exactly equal to the chemical potential in our gas phase at this boiling point. And the chemical potential of our solution over here on the left in the liquid phase, that's going to be our mu naught at that temperature and pressure, again minus this correction factor NB KT over NA. This is the correction for the presence of solute molecules, and on the right hand we just have the usual gas or the usual chemical potential for the gas at that same temperature and pressure. And the methodology we're going to use here to examine this effect is basically the same methodology we used over here for the osmosis. In other words, we're going to assume that this effect is relatively small, that's going to have a modest change on the chemical potential, and then we're going to expand our chemical potential basically in terms of the other variables that could be affecting it. In particular, we're going to expand it in terms of the chemical potentials of our, we're going to expand this chemical potential in terms of a modest change in the chemical potential here, and we can look at it in terms of either a change in the pressure. It's going to change the vapor pressure at which we boil our solvent, or it's going to change the pressure, the boiling point, the boiling temperature, and we can look at either the vapor pressure change or the temperature change, basically looking at how far does it push it to the right on a phase diagram, or how far does it push it vertically upward on a phase diagram, to the right or the left on a phase diagram, or up or down on a phase diagram. So we're going to make a linear approximation here again. And so again, the equilibrium condition is that we're going to look at first. Let's look at the pressure question. So we're going to say that P naught is the vapor pressure of our pure A substance, so the pure solvent. Of pure solvent, and thus that mu naught at T P0 must equal mu gas at T and P0. In other words, this being the vapor pressure, the gas pressure of our pure substance, or the gas chemical potential of our pure substance, must equal the liquid chemical potential of our pure substance. And that, plugging that back in over here, then we can say, or we're going to say then that we're going to expand our chemical potential for the solution in terms of mu naught and T at P naught, not our T of P here, but T of P naught, plus a linear correction term, P minus P naught of d mu naught dP, minus this NB KT over NA term. That's going to equal, now we have to expand this gas term also around P close to P naught. So this is going to be mu gas at T and P naught, plus again a linear correction term, P minus P naught times d mu gas dP. Right, so we've expanded both the chemical potential of the gas and the chemical potential of the solution, or of the pure substance, in terms of pressure, assuming that it hasn't changed the vapor pressure a lot, that these are small enough that we can truncate basically our Taylor series to simply the linear terms. Now, because at P naught the mu naught, or the chemical potentials must be equal, then the first term on either side of this equation cancels, and so we can rewrite this as the pressure difference, or the pressure change, times the derivative of the liquid chemical potential with pressure minus the solution term here, NB over NAKT, and that's got to equal again the pressure difference, or the pressure change, or the change in the vapor pressure by the change in the gas potential energy with respect to pressure. And we just saw over here that d mu dP tends to be a term in V over N. So we can replace the d mu dP terms with V over N terms for the appropriate phases. And so this becomes the change in the vapor pressure times the volume per particle in the liquid phase, minus NB kT over Na, that should be an Na up there, is equal to the change in the vapor pressure times V over N for the gas phase. V over N for the gas phase, if we just assume an ideal gas, then this gives us kT over P naught. That's an ideal gas from the ideal gas law. And as a first approximation, we're going to assume that the liquid phase is very, very much denser than the gas phase, which is true for most gas or most boiling phase transitions. And so we're just going to assume that this is very small compared to this term. And essentially then this first term here will essentially drop out. And we'll be left with minus NB KT over NA is equal to P minus P naught times KT over P naught, which we could then cancel the KT terms, bring the P naught over. That would give us minus NB over NA times P naught is the change in the vapor pressure, or that the vapor pressure divided by P naught is equal to 1 minus the ratio of NB over NA. This is called Raoult's law, and says that the ratio of the new vapor pressure, the vapor pressure in solution to the vapor pressure of the pure solvent is just 1 minus this ratio of the concentration of the solute to the solvent. And suggests that the effect of adding a little bit of solute to our solvent is to decrease the vapor pressure. That the amount of pressure you would need to have to keep a solution in liquid form is less for solution than it was for pure substances. And again, you can kind of think of a microphysical reason for this to happen because again, if we think about sort of boiling is happening because every once in a while you get a high kinetic energy particle from our liquid phase bursting across the surface and flying up into the gas. Most of those collisions will be solvent, but every once in a while, instead, the high kinetic energy particle will be the solute molecule. It's not going to have enough to push it out into the gas phase, and so that collision against the surface of our liquid won't every once in a while won't incur a boil, won't incur the loss of that molecule to the gas phase. And again, the ratio of those things happening is going to be the number of B molecules to the number of A molecules. So this kind of makes a bit of intuitive sense from that sort of microphysical model of what's happening at the boiling point. The other thing we could do is examine this in terms of how it changes the boiling temperature, the boiling point. So we're going to vary the temperature instead of the pressure. We're going to say that T naught is the boiling point of our pure substance, of our pure solvent, which again says that the chemical potential of our pure solvent at T0 and whatever pressure we're at has to be the same as the chemical potential of our gas phase at that same temperature and pressure. But that again, in our case, our solution has a chemical potential of T0 at some T plus or NP minus this solution term NB KT over NA, and that's got to equal the gas chemical potential at the true boiling point and pressure of our solution. So this is the pure solvent EQ condition, equilibrium condition, and this here is our solution equilibrium condition. And the temperature here would be our new boiling point. And we're going to again make the same assumption that this correction term is relatively modest, that the effect of the boiling point is going to be pretty small, and in other words, that we can expand each of these chemical potentials in a Taylor series that again truncates at the linear term. So we're just going to expand this out to linear in the change in temperatures, that we're going to say this mu naught at T and P is actually mu naught at T naught, P plus a linear term in temperature, change in temperatures, change in the boiling point temperatures times d mu naught dt, again minus our solution term NB KT over NA, and we're going to expand the gas side in the same way. Chemical potential of the gas at T0 and P plus a linear term in temperature, T minus T0 times d mu gas dt. Again, from the pure solvent equilibrium condition, the first two terms cancel each other out, and we're just left with the two terms here on the left and this term here on the right. The change in the Gibbs free energy with time is minus entropy, and the Gibbs free energy is again n times mu, and so d mu dt then can be thought of as minus the entropy per particle of our system. So again, we can replace each of those derivatives with minus entropy over n. So this is going to give us a minus T minus T naught times entropy over n in the liquid phase, minus NB KT over NA is minus T minus T naught entropy per particle in the gas phase. Let's go ahead and divide out the number of particles across the board, and we'll collect the temperature difference term over here on the left. So minus T naught times the entropy in the liquid phase minus the entropy in the gas phase equals NB KT. And we're going to suck that minus sign on the inside, so T minus T naught of the entropy in the gas phase minus the entropy in the liquid phase equals NBKT. This change in the entropy from gas to liquid, well, that's T times that change in entropy, right? T times this delta S here would be the latent heat. So that this delta S is just our latent heat divided by the temperature. Again, it's going to be NBKT. And so our temperature difference here, T minus T naught, is going to be NBKT T naught over our latent heat. And again, we're going to assume here that T is almost T naught, so that this is approximately NBK T naught squared over the latent heat, or writing it in molar form, little n b r T naught squared over L. And thus, the effect of adding a little bit of solute to our pure solvent is to increase the boiling point by this amount, NBKT squared over L, or little nbr T naught squared over L. So let's think about, for instance, how much does the salt in salt water affect the boiling point of water? Well, the latent heat of water is 2260 kilojoules per kilogram, and a kilogram of seawater contains something like 35 grams of salts, which comes out to roughly, at the typical molar masses of salt, that comes out to about 1.2 moles of salt ions dissolved into our water. And so the temperature shift for our boiling point is going to be roughly this 1.2 moles of salts dissolved into our water. The gas constants here are 8.3 joules per mole per Kelvin, multiplied by the boiling point of water squared, so 373 Kelvin squared, divided by the latent heat of water, 2260 kilojoules, and that comes out to about 0.6 kelvins or so. So in other words, seawater boils about roughly half a degree Celsius or half a degree Kelvin above the boiling point of pure water. It's a pretty subtle effect. Again, we expect it to be. The whole point here of the dilute solution is that these terms should be relatively small. And again, there will be a couple of interesting homework problems to investigate this a little bit further. All right, that's all for today. Next time we will look at chemical reactions.